everybody. Thank you for inviting me. I won't be talking about the intelligent reflecting surfaces. I mean, I have a couple of slides, but this talk will be on deep learning. And in particular, I will, I guess, give a brief overview of deep learning. I'm aware that you may be all experts about it, but just to get the right terminology, just in case, I will be briefly recapping what is a neural network and how you train a neural network, standard methods. Then this is basically the main contribution, the main idea, and it's about how to use neural networks coupled with traditional model-aided approaches, so optimization, purely optimization theoretic approaches, to solve resource allocation problems. In particular, I will be talking about power control problems. There's also one discrete problem, but mostly it's power control. And then I will present some applications. I will try to be brief. If you want more details, you can refer to this work, or you can email me. Okay. So, okay. I guess you are all aware about the difference between AI, machine learning, and deep learning. And this talk will be just on deep learning, which is a specific machine learning tool, which implements the learning process through neural networks, deep neural networks. And why deep learning? There is no conclusive proof. So I'm not saying that you should use deep learning in deep networks because the rest is not good. I'm just saying that typically, okay, this can be proved. So neural networks are universal function approximators under very mild assumptions, which means that a priori, you don't set any functional form for the model you want to learn. The network learns it for you. And it seems, I mean, numerical evidence shows that typically when you have large data, neural networks deep learning performs better than classical learning. But nevertheless, this talk will be about deep learning, so I hope I'm not offending any machine learning guy here who doesn't like deep learning. Okay, so what is a neural network? Again, I'm sure you all know. I will be focusing on feed-forward, fully connected neural networks. So there are layers. You have the input layer is a vector of numbers. The output layer is another vector of numbers, and fully connected, each neuron is connected to all neurons in the following layer. And there are a series of hidden layers. They do some processing layer by layer. So input data, first processing here, then second processing here, and so on. And at the end, you get the output for a given input. What does each neuron do in this model of neural network? It's very simple, and there's only one point that I want to stress here. So each neuron takes as input, as we have said, a vector, which is the output of the previous layer. Let's call it x. And then it takes an affine combination, so scalar product with a vector of weights that depends on the neuron. So each neuron has its own weight, plus a bias term. So this is a fine, very simple affine combination. This result then is the argument of what is called the activation function of the neuron. And the activation function, I have a list later, but there can be many, but they are all elementary functions. So no integrals, no complicated stuff. What do I want to say by this? I want to say that the processing that each neuron does is actually very simple. So computationally speaking, the complexity is negligible. Okay? And if you consider the output of the neural network as a function of the input, you can actually, and the weights and bias have been already configured, you can actually write down a formula that gives you the output as a function of the input by composing all these terms for each layer. It will be a horrible formula, I mean, very cumbersome, but it's a closed form, okay? This, of course, if W and B are fixed for every neuron in a network. So this is somehow obvious, but it will be important later, okay? So what I want to say is that a neural network, if it is already trained, and then we talk about training in a second, it gives you a formula, a function that gives you the desired output given an input, okay? Oh, if you have questions, just stop me, so don't wait the end of the talk. Okay, so this is a list of activation functions. It could be linear, even though, as you probably know, you should not use only linear functions, because otherwise the network can only give linear maps. Then you have a sigmoidal functions, hyperbolic tangent functions, and up to the most advanced ones, so the most commonly used, which are the ReLU, you all know. And then the ReLU also has some generalization, because in some cases you don't like that the ReLU is 0 for negative inputs. So this generalized ReLU basically has the output for negative inputs is not 0, is a line. And here the exponential linear unit for negative input, you have basically an exponential function. And then for positive unit is always like the normal ReLU, okay? Again, as you see, these are all elementary functions, okay? So computing the output given the input is a very straightforward and simple task. This is if you know the weights and bias. So how do you, it's stuck, okay. How do you, okay. How do you train a neural network? Okay, let's first give these two results, which are not, quite old, 1993. And this is probably the only theoretical results that you have in neural networks, which tells you that every continuous, in a simplified statement, every continuous function can be emulated as input-output relationship of a neural network, okay? This will be the property that I will be using in the application part of the talk. There are bounds of the neurons number of neurons that you need to use to get a given approximation accuracy, but this result here is not constructive. In which sense? It tells you how many neurons you have to use, but not how you have to organize them and arrange them. So it's like the capacity theorem. There is a coding-decoding scheme that gives you capacity, but you don't know which one that is. And but at least this gives us hope in the sense that we know that it can be done. Then it's just a matter of finding the right architecture, okay, when we want to approximate a function. And why do we need this property to solve optimization problems? It will be clear in a while, okay?
The theorem is about one layer.
Sorry?
The theorem is about one layer network, right? This is not
yes, but if you take 0 weights for all the other layers, it's like, so one layer is a special case of a deep network. So if it works for one layer, it works for all, you can always go back to one layer, okay? And this has not been proved. It's just experimental evidence that normally if you have deep architectures, you require less neurons to approximate your function, okay? Okay. So how do you do the training? I guess this is also standard knowledge for you. So the typical approach is supervised approach for neural networks. In general terms, you have a training set of inputs with the desired output corresponding to this input. And you want to optimize all the weights and bias in your network, so all the parameters, in order to minimize the loss, the error between the desired output and the output that your network gives you, okay? And you want to optimize this data, which is basically the network parameters. This problem, if you look at this from an optimization theoretic perspective, it's tough in the sense it's not convex in general. Okay, here you can have several choices, but in any case, the output of the network as a function of the weights and bias is a complicated nonlinear map. So solving that problem optimally is tough. And then the number of parameters is quite large. You have lots of weights, lots of biases. So what you can do, normally you do stochastic gradient descent method, so first order method, and okay, with backpropagation to compute the derivatives. Okay. Okay, stochastic gradient descent. So what does it mean? You get your training set, you partition it into mini batches, and you do the gradient. You evaluate the gradient on each mini batch. You do it for all mini batches, and that gives you one epoch of training, and then you start over. Okay, so this is the algorithm. Of course, stochastic gradient descent doesn't give you any convergence guarantee, in the sense that it can oscillate because it's stochastic. But again, it's been used for it's used in all applications basically. And if you use any commercial software like TensorFlow or Keras or anything, they implement this stochastic gradient descent method. Okay. There are ways to improve the convergence of the stochastic gradient descent. One is to use momentum. So this is the original reference. And this is a known method from optimization theory. So it's not something that has been developed for deep learning. It's something that was developed a long time ago. And it's just like stochastic gradient descent. And it's something that smooths out the oscillations of gradient descent, of stochastic gradient descent. Okay, you have to configure this parameter v, which is called the velocity of the method. I mean, I'm not going into the detail of the mathematical details of this approach. Just know that it can be used. Like it, as far as I'm aware, the Adam algorithm is among the standard methods that you find in solvers. This is the most advanced, and it exploits not just the gradient, but also the squares of the gradients. And this is more recent, 2015. And I'm reporting it just so that you know, in all applications that I will discuss later, we have used this method. Okay, so all the training that we do later will be done by this Adam algorithm. Okay. Initializations. Okay, this is, I want to spend a couple of words here because it will be important when I explain the framework later. So when you solve the training problem, so you have to solve this non-convex problem. Of course, any algorithm, any iterative algorithm, you have to specify the initialization. Okay, and in deep learning, you find papers which propose a lot of different initialization rules, and it's not clear. So there isn't one initialization that is always better than any other. So you have to try. But if you, I don't know if you work a lot in optimization theory, but in optimization theory, when you have a non-convex problem, selecting a good initialization really makes the difference from finding a good solution or not. Because otherwise you can get stuck in a very bad local minimum or not. So selecting the initialization for your stochastic gradient descent is an important point. And in a sense, the method that I will discuss later is an efficient way of selecting a good initialization point. Okay? But if you want just the references for classical initializations, I mean, you can refer to this references here. And yeah, so this is it. Okay? I guess this is all things you already are familiar with. Okay, then there was a talk before about regularization, so I guess I will also go very fast here. So you know about the problem of overfitting, right? So everybody Does anybody know? Does anybody ignore what overfitting is here? Okay, so there are several regularizers that you can use to avoid overfitting. Of course, there's this LP regularizers where you add this norm P perturbation to your training function. And of course, as discussed in the previous talk, you can have L1 or L2 regularizers. I just want to say, I mean, we haven't used these regularizers in our applications. In the sense, I mean, we have tried them, but in the end, we have used this early stopping. So have you heard about this early stopping? So it's actually very intuitive. So when you train a network, neural network, as you go on with your gradient updates, your training error goes down, okay? At some point, I mean, at first you hope that your validation error also goes down, but at some point the validation error might go up again and you go in overfitting. So early stopping just tells you when you, very heuristically, when you see that the validation error goes up, just stop training, okay? Don't take too many gradient updates because it's useless. You are only improving the training error, but your validation error may not improve. And I'm mentioning this because, so in all applications that that I will be presenting later, we have found that this was the most effective, okay, rather than most effective, we have also tried L1 and L2. Basically, we get the same performance. Okay, so in the end, we have used this, which is simpler, so less complex. Okay, clear? Yeah. Yeah.
These functions are usually very noisy. In my experience, it's very difficult actually to calibrate every stopping. So how do you go in the
trial and error? Trial and error.
But how do you get rid of the noise? You have any technique that you use?
Okay, one thing that we have tried, but again, so in my experience, it doesn't really change your life. So you can launch the training with different initialization points, and then you average the results. And this somehow removes the noise. Because
so train several times.
Train several times, and then you take an average configuration. But again, from my experience, this didn't change much the performance. So the performance was exactly more or less the same. We have used it for one applications. We have used it. So the results that I will be presenting later in one applications use this method. But it's not that it doesn't work if you don't use it. So this is what I wanted to mention. So in the end, we have seen that regularization, at least for power control problems, doesn't really impact your performance a lot. But of course, I cannot make any general statement. Okay, so another point is how do you select your neural network architecture? So we had a talk in the morning, and you can use meta-learning. You can use other methods. Here I just mention standard approaches, because in the end, again, we haven't used any advanced method for architecture selection. We have just used our eyes, basically. So look at the learning curves. This gives us this has given us good performance. And in general, there are several frameworks that can help you with a neural network hyperparameter tuning. What I mean here by no theory for hyperparameter setting, it's just that there is no theory that can really give you a guarantee. This is the optimal architecture that you have to use. And there is no other architecture that is better than this one. Of course, there are frameworks that can find you optimized architectures. And I encourage you to use them, but it all depends in the end of how much complexity you can sustain. So if you want, what we did was to use a very simple tricks, okay? And I will discuss later in a moment. So this is basically what we have done. So when we train the network, we just check the training error, and then we increase the capacity of the network until the training error is good. And then we check the validation error, and if it's too high, we decrease the capacity of the network until we find the optimal trade-off. Okay? In many cases, this has worked. Another approach is start from a very large network, so very large capacity, and then try to reduce the size of the network as much as possible until you get good performance. And this has given us quite good results with simple setups. Okay? So we haven't used any sophisticated architecture searching tool here. Okay? So basically it's trial and error, but with some insight. Okay? Clear? So this was just to get us started. All simulations have been done with this tool here, Keras, which uses TensorFlow, basically. And it's developed in Python. I mean, if you're good at coding, you may not want to use this. So you want to code your Python code yourself. If you are like me, I have a communication theory background. I have used MATLAB all my life. Then when I started doing this, I didn't know anything about Python, and this was a nice entry point, okay? Because it gives you a lot of built routines that you can just call without knowing a lot about Python at first. Of course, if you want to do more advanced stuff, in the end you will have to learn Python. But as an entry point, I suggest this one. Then once you have this, you can go deeper and develop your own training algorithms. Okay? So this was very brief introduction, and now if you have any questions, even though I think this was all basic stuff for you. So let's start talking about more research-oriented things. How do you use neural network to solve a resource allocation problem? So what do I mean by model-aided deep learning for wireless networks design? Okay, so general statement of an optimization of a design problem. You have some input parameters, and you can think of them as your channels, the channels of a wireless network. And the output is, for example, the optimal results that you want, for example, the transmit powers. Okay? So you have a wireless network with some users. Each user has some channels, and you want to know the optimal powers with which each user has to transmit. Okay? This is traditionally done by optimization theory, at least. You have the objective function that you want to maximize, for example, the sum rate, or you want to minimize the mean squared error, whatever. And you use some optimization frameworks to really solve this optimization problem. The point is, this requires a mathematical model of your wireless network. Okay, so a function that you want to optimize. So the problem is that there's a trade-off here. So if your model is too difficult, too cumbersome, the optimization is more difficult. So the complexity will be higher. Of course, you can try to simplify your model and make it into a very simple formula, but then you are making a big approximation error. Okay? So neural network can help in this respect because they can actually provide way to solve very complex optimization problems. Okay, and I will talk about this in a second. Also, you have to do this. Normally, you need a lot of data to train your neural network. But what I mean by model-based is that if you exploit your theoretical knowledge of the network, even if it is approximate, even if the model is not completely 100% accurate, this can be used to reduce the number of the size of the training set, basically. So it represents prior knowledge that you have about your system. And if you have some prior knowledge, you don't need a lot of training data. Okay? I will be discussing applications in a second. These are just the slides about reconfigurable intelligent surfaces that we discussed at lunch. And this is just an example I'm not talking about reconfigurable intelligent surfaces. I don't want to enter a discussion about this. I'm just using this as an example of how complicated an optimization problem can be. Okay? So what are reconfigurable intelligent surfaces? If you don't know, they are like very thin sheets of special material, which is called metamaterial. And this metamaterial is basically has resonating elements spaced at a sub-wavelength distance. This makes the material capable of reflecting electromagnetic waves without being bound to Snell's law. Okay, so normally if you have a wave that impinges of that surface, the reflection angle must be equal to the incidence angle. This is Snell's law. With this material, you don't need to do that. So you can design the direction towards which your electromagnetic field is reflected. Okay? What can you do with these things? Well, in principle, you can do lots of stuff. For example, if you want to, this base station wants to reach this mobile, and there's an object here that blocks your path, you can configure this object in a way that the signal goes here, and then the reflection angle points towards the terminal that you want to reach. Okay? Another thing that you can do, if now same scenario as here, but you have a device that is a device that doesn't belong to your network, so should not receive the signal. And if you do it like that, this guy would receive a signal that maybe it's not intended for him. You can design this surface in a way that it absorbs the radiation and doesn't reflect anything. Okay? Now, this gives you a lot of opportunities. Of course, you can imagine that the design of a network like this might be very complex because you have a lot of new variables. So you have to design the transmitter and receiver as you always do. And then you also have to design all these phase shifts, all these angles. So the number of optimization variables is growing larger and larger. Okay? This is just an application, an example. And I'm not going into the details of this approach. All the applications that I will be discussing later will not consider these meta surfaces, and already the problems will be quite hard to solve. Okay? Okay, so to repeat again, the table there just shows what typically is the situation when you have to optimize a network. So you can either have a network where you have a very accurate model, theoretical model of the network, and this accurate model is simple, so you can optimize it. Or you have models that are intractable and inaccurate, and in this case, you are basically out of luck. But the two cases that are most common in wireless networks are actually C2 and C3. So unlike other fields of science where you use deep learning, like image processing, speech recognition, where basically they don't have any theoretical model of what they want to do, in wireless network we do. We have models, okay? It's just that either the model is too difficult to optimize directly, or it's tractable, but only because we have made a lot of approximations. Okay? And in these two cases, neural networks can help if we also exploit the prior knowledge that is given to us by the model. Okay? Okay, so we propose two approaches. Okay, maybe I will just do it here. So let's focus on C2. In this case, you have a model. Having a model means that you can formulate the optimization problem that you want to solve. You can write it down. But then it's too complex to be solved directly. It's not convex, and then you want to use global optimization methods, but it's not practical. What you can do, you can train a neural network to find the solution. Okay? It will become more clear, I hope, when I present the applications. But basically, what we are doing is, it's not that the problem cannot be solved. It can be solved, it's just that it's too complex. So when you can't use it in a wireless network. Okay? But you can build a training set by solving the problem offline for a lot of channel realizations. Okay, it will become clear with the applications. You train a network, and then once you train the network can just predict the optimal resource allocation. Okay, probably it will become clear later. I don't know if you have any questions at this point. Okay, then the other step instead is refining a model. So in this case, we focus on C3, where you have a model, and it's simple. You can optimize it easily, but it's approximate. Then you can use a neural network to refine the solution that the model gives you. Okay. Okay. So let me try to say it again. So here we have a wireless network, and we have a mathematical model for the network. So let's say that we want to optimize the sum rate. We can write down the formula. It's just that it's complex. So you can solve it, but then you cannot really deploy the solution online, because it will take a lot of complexity to solve it, and then as the users are moving, the solutions becomes, so you should resolve the problem every time the channels change, and that's too hard. So we train a neural network to learn the solution, and then once the neural network has been trained, it will give you a formula to predict the optimal power allocation. Okay. For the other case instead, okay, let's do it directly here. Now we have a model that is only an approximation. So what we do, we first use the same approach as before. So we train a neural network on the approximate model. Okay. And we get an approximate system design. And then by using a specific approach of transfer learning that I will discuss in a moment, you basically refine this the configuration of the neural network. So what we do here is the following. So if you recall when I said that finding the initialization of your weights and bias is important when you train the network, that's exactly what we are doing here. The first training that is done on the approximate model, which is simple, it will give you a configuration of your weights and bias, but it's an approximate configuration. However, you can use this configuration of weights as the starting point for a second training phase, which is done on empirical data. Okay? I don't know if this is clear enough. Okay, I see some confused. So is it too simple or too hard?
It's like meta learning, right? Because we have some kind of initialization points and we are trying to...
Yeah, but the initialization point that you get it from a mathematical model.
Yeah.
So so meta learning is so the bigger picture is transfer learning. So this is an approach that is called network-based transfer learning, and it really tells you to do this two-step training. First, you train the network on your approximate model. You get an approximate model of the wireless network. This gives you an approximate configuration of the neural network. And then you have to refine this configuration with empirical data. So what is the advantage? Because you can tell me, okay, but if you, so in this case, if you only use, maybe I didn't stress this point. So in this case, the advantage is that if you have a model, you don't need to do any measurements. So one critical point in when you want to build a training set is that you should actually go out and measure data. This might be difficult to do it. Here, if you have a model, you can generate synthetic data, okay? And in this case, you don't need any measurement, any empirical data at all. So you can generate as large as a training set that you want. In this case, it's more tricky because your model is not actually the reality. It's an approximation, and it's a crude approximation. Okay, so you can generate a synthetic training set, and this gives you a rough training of the neural network. Then you should have, and we will, the application, I will give you some numbers, at least for that particular application. But the idea is that the training set that you use here to refine your configuration is a lot smaller than the training set that you used for the first training phase. If it's not like that, this is useless, okay? The idea is that if you know a model, even if it is approximate, it contains information that can tell you how to find an approximate configuration, so that when you train based on your empirical data, you don't start from scratch. You start from a point that is already good enough, okay? Of course, let me just stress this. So I'm not saying that there's a mathematical theory behind this that tells you this works every time, okay? Of course, there are a lot of hyperparameters here. How large should the first training set be? How large should the second training set be? This is not known. You have to try, okay? But the idea is that this training set is a lot larger than this. Okay, so in the simulation, the case that I show later, this will be 10 times larger than that. Okay. Okay, I hope I didn't confuse you enough, and I hope that now that yeah.
Basically, you generate synthetic data with, let's say, a length
that you like, yes. Yes.
And then you get some kind of weights and biases.
Yes.
Number of layers and neurons and those stuff for that specific data, and then you retrain by taking that as a starting point with real data.
Yes, exactly.
So that's
exactly. Yeah, exactly that. Yeah.
So it's something like few-shot learning,
Few.
one-shot learning, or
okay, this is not one shot because it's
few
shot. Yeah, okay, two-shot learning, two-shot learning. Okay. Yes, two-shot learning, and let me just say that. The general idea, so when I went very fast on this, the general idea is to use this deep transfer learning, which you can read about here. And this is really a framework that tells you if you learn how to do something that is not exactly what you want to do, but is related to what you want to do, and then how do I exploit this knowledge to learn the second task, which is called the target task. And the previous one is called the source task, so that when I learn how to do the target task, I don't have to start from scratch. And this two-step approach is one possibility. So it's the one that in our case worked best. There are other, so in this case there are at least 4, in this paper there are at least 4 approaches. Another one, I just mentioned it uses GAN, generative adversarial networks. But I mean, in our case, this two-step is the one that was at the same time, as always, as I said, we tried to develop simple algorithms. So this is conceptually quite simple, I would say. So I first course training and then I refine, okay? And it worked quite well, actually, okay? Yeah.
Basically, another thing that I comment is that you, get those parameters, and then you frozen that architecture and then perform feature extractions, or you retrain it?
No, I retrain the network with a new training set, but I freeze the structure. Yeah. Okay. Yeah. Exactly. Yes. Exactly. Yeah, of course. That's what I said before. This is no, so there is no. No, let's go here. Of course. So here you get an approximate configuration of the network, and if the model is accurate enough, then this approximate configuration is hopefully in the right direction. But of course, it can happen that if there's a big error in your model, you are actually having what is called a negative transfer. So actually, the first training just screws things up completely. This depends on how accurate your model. So what I'm saying is, the assumption is that your model is not just something that you assume, so it needs to be done with a criterion. So you assume it, but it needs to be at least partially realistic, okay? So this happens all the time in communication theory. So you have a model, and then it's too complex, and you say, yeah, I neglect this term because it's a second-order term. And of course, this may work. If you oversimplify, then it doesn't work anymore.
This portion of this training over this actual data may be one, and the synthetic data, how big is it?
This depends on the application. Actually, there is no mathematical formula for that. So in our experiments, this was 10 times bigger than this. For the specific case, that was a very simple one. We had 30,000 synthetic data and 3,000 measurements. Okay, but that is a very. This will be the last application. It's a very simple problem. Okay, very simple problem. I mean that the input of the neural network is only one neuron, and the output is one number. Okay, so that's why we had 30,000 and 3,000. If you consider larger inputs and outputs, you need a larger training set. Yeah. Okay. Any more questions? Okay, so I hope that with this first application, things become a little bit clearer. So the problem here, consider a generic interference network. So interference network means K transmitters, M receivers, and they all interfere with one another, okay? You have multiple antennas at the receiver, single antenna at the transmitters, and your goal is to find to allocate the transmit powers of each user, okay? If you write down the SINR at a generic receiver, is this, where this is the receive filter, this is the channel, and these are the powers. So the powers are your optimization variables, which means that this and this are just coefficients. And so you can write the SINR like that, where AK and BKJ are these numbers here, which are constants for you. Basically, they depend on the channels, and they will become the input of your neural network. The output, so what your neural network should do, is to find the optimal P for all users. Okay, so it's a vector of K numbers. Find the optimal P for what? To maximize that function, which is called the sum energy efficiency, and is the sum of the energy efficiencies of the different users. Okay, so the rate divided by the transmit power, that is called the energy efficiency, and then I sum that for all users. Why did I select exactly that function? So if you are familiar with energy efficiency optimization, you may know that that is not the most common energy efficiency function. A more common one would be to have the sum of the logarithms divided by the sum of the powers. That is called the global energy efficiency. And it's, from a physical perspective, it would be more justified to consider that. But I consider that because that problem is more difficult. So when it comes to fractional programming, so optimizing fractions, the sum of fractions is one of the worst objective functions that you can have. Okay? That problem there is NP hard, NP complete, any nasty thing that you can think of. Okay? If you consider max-min problem, for fractions is easier than that. Okay? So showing that a neural network can learn the optimal power control to maximize that means that it should be able to find the optimal solution also for simpler problems. Okay? So how do I formulate the problem? Maximizing that function with respect to the transmit power with some constraints, maximum power constraints, you can see it as the problem of finding a map between the channels A and B, which I recall are these numbers here. The problem parameters, so the maximum power that you should have, and the optimal transmit powers. Okay? So you are, if I give you A, B, and P max, I am specifying one instance of the problem, and I can ask you to find the optimal powers. Okay? So I told you before, neural networks are universal function approximators. Of course, nobody tells you which neural network can approximate that function. You have to find it. But it exists. That's the point. So there exists a configuration of a neural network that takes as input A, B, and P max and gives you the optimal power allocation. Okay? Clear? So this is the general idea. Of course, how do you do this in practice? So this is a little bit controversial for the following point. You can ask me, yes, okay, this is true, but you have to train the network. To train the network, you need to have a training set. How will a training set, so what will a training set look like here? It will be a set with realizations of A, B, and P max. So one point of the training set is one realization of A, of B, of P max, and the corresponding optimal power. This is one entry of your training set. To train the network, you need a lot of entries like this. Okay? And this, how do you find them? How do you find them? Because you haven't trained the network yet. Sorry? Yeah, simulating, but it will take, so basically exhaustive search, you can do that, but it's a lot, I mean, it's really tough, because basically I'm saying to generate one sample in your training set, you have to solve an NP-hard problem, okay? So you might be saying, okay, then you said that this would simplify things. Are you kidding me, or what? Yes, but the point is the following. The point is the following. If you want to solve the problem online means when the system is operating, then forget it. This is too complex. But you can, what you need to do here is to solve it offline. So the training set doesn't have to be generated while your system is working. You just do it offline. It will take you some time. I will tell you how long it took for us. But you can generate it offline. You train your network offline. Then the only thing that you do online is the forward propagation with the already trained network. Okay? And as we discussed at the beginning, this is really simple. Just linear combinations and elementary functions evaluations. Okay? So finding this map is hard, but you do that offline. Once you have this map, you have basically a formula that tells you, you give me the channels and I give you the optimal power. Optimal, I mean up to the approximation error. Okay? And this is what we did. So in this slide, I basically have summarized what I just said. There's only one more point that I want to discuss or mention. To solve this problem, actually, this problem here, we developed a specific branch and bound method. So I won't talk about this because it's not related to neural networks, not directly. But it's an optimization method, global optimization method, specifically for that problem that works a lot faster than general purpose branch and bound. And these are the numbers that we get. Another point that I was forgetting. The training, how often do you need to train your network? Of course, this depends on the mobility of your environment. As long as the distribution of your channels doesn't change, you don't need to retrain. Of course, as the users move, the distributions will change. And then you need to retrain the network. But for sure, you don't need to do it in every coherence block. Okay? And in a moment, I will show you results to show that even if the channels distributions change and you don't retrain, the neural network is quite robust. Okay? Let me go to the numerical results. That's the architecture that after a lot of trying was the one that gave us better performance. So 6 layers, neurons, and activation functions. We have used Keras, Adam, and we use the MSE as training cost error. The training set, so we generated basically 102,000 training samples. So basically we solved the problem these many times. That is the validation set. The test set is very long. So we generated 10,000 samples for each value of SNR from -30 to 20 dB. In total, we had to solve that NP-hard problem 622,000 times. Okay. In this case, so these numbers are for this rather small setup. So we have a network with 4 users, okay, and 2 antennas each. And for now, forget about the shadowing part. For now, we only have fast fading and path loss, okay? Still, try to solve 622,000 NP-hard problems with 4 variables. It's not so simple. It took some time, but on a normal computer, it took not even 9 CPU hours with the branch and bound method that we have used. And this is just the learning curve, so the training loss and the validation loss. This is just to show that with the neural network the architecture that I showed before, so you don't have overfitting or underfitting. Okay? Get into the results now. So Pmax and your objective function. The red line is the optimal. So when you use branch and bound to solve the problem. The ANN is the blue line, and it's basically performing like the optimal. Of course, I mean, if you zoom in, there is a very small error. But still, this other line here that I call SCA, SCA stands for sequential convex approximation. It's one of the state-of-the-art methods to solve this kind of problems. And okay, without really entering into all the details, let me just say that this is the SCA, and this is another version of the SCA. It's just that this one uses a much more complex initialization rule than this one. That's why this performs a lot better than this. Still, it's less than the neural network. Okay, there's a small gap. These other two are just benchmark solutions when transmit with full power, so no optimization basically, or only one user transmit. Okay. Now at this point I get several questions usually. So I get first several people ask me, are you saying that you found a way to solve an NP-hard problem with negligible complexity? The answer is no. I'm not saying that for two main reasons. First, we didn't solve the problem in the sense that I'm not able to give you a guarantee that the solution given by the neural network is optimal. I can show it to you by simulation, but it's no theoretical result. Even more than that, the complexity is not small. It's just that I divided the complexity in two parts, the offline part and the online part. The offline complexity is huge. You have to generate the training set. What is small is the online complexity, which is in the end what you care if you have to run a wireless network. Okay? Then other questions that I get are, okay, this is for users. So this is quite simple. What happens if you increase the number of users? Well, we went up to 7 users. Results don't change much. Now, except that now there is a small gap between the neural network and the optimal solution. And basically the neural network performs like the SCA method. But the SCA is the online complexity of the SCA is a lot higher. So the SCA solves the problem through a sequence, so it formulates it as a sequence of convex problems. And so you have to use the interior point like several times, like 10, 20 times. Okay? Another question that I usually get is, what happens if you have a mismatch between, so because you train the network with some channel distribution. What happens if the channel distribution change? Then here we use the network that we trained before, and the training set has no shadowing. But then in the testing phase, we used some shadowing. So the channels that we use for testing include a shadowing term, but those for training didn't. And of course, you have a gap, okay? So gap between these two and gap between these two. But, okay, these two are, here you have only shadowing added. Here you have shadowing plus a more complex fast fading model. It's not really important to enter into the details, just to mention that the mismatch here between testing and training is larger than here. Okay? And of course, there's a gap, but I would say that, I mean, I would be happy with those results. Okay? Okay. So I guess I'm done with this. You have, yeah.
It's not a question, but more of a recommendation. You said for creating the training set, you had lots of trouble because you need to solve many instances of this problem. So which I counted like
well,
optimization. You have set up parameter, and
Wait. The training set, the problem is not convex, but the training set is optimal. We use branch and bound. That's a global optimization method, and that gives you a guaranteed optimal solution. It's just that it takes time. So it's not polynomial complexity. It's exponential complexity, but the samples are optimal. So the power that we use for training are optimal.
Can you come back, for example, 5 slides before once you were clear?
This one?
This slide you were explaining how we increase training.
Here? Here.
For example, here about the things we did, the similar problem we are tackling, for example, for state-free uplink, exactly the same problem. We have a parameter, we want to produce power allocation coefficient.
Okay.
But here the things we did, instead of solving this many instantial problem, we consider we can, what is our objective? At the end we want to minimize our cost, the cost, for example, of sample.
So you use that for training cost function.
We replace the cost function of neural network
With that.
and we try to train neural network directly. You don't need to create.
It's true, but when you do that, you cannot guarantee optimality. Because
In this way, if you want to guarantee optimality, you need to.
it's more complex. Sure. So, yeah, if you don't care.
The complexity by order of the 2 orders, 3 orders of magnitude.
It reduces the complexity a lot, but the problem is that this is done offline, so we don't really care too much about this complexity. That's the point.
So if you want to increase 4 users to 40 users, you can't do it.
40 users, I mean, you can do it, it's just how long it will take.
Like 6 months, for example, with this approach, because it's not scale.
Depends how many computers you have, how many. I mean, of course, if you can go up to 100, 200 users, it will be more challenging. I know. I agree with you. It's just that so you are trading off complexity with performance. That's what I'm saying.
The things which, I mean, this is a nice approach for first line, it's used as a baseline, but about the commenting, you can directly minimize or maximize the cost, the objective you have here without producing this data set. So
It's true, but then you cannot claim any optimality.
you can compare with the optimal solution.
compare.
I am this far from the optimal solution.
True. Anyway, yes, you can do it. So what I'm saying is that the only thing is that you can claim optimality. If you don't care, yes, you can do it and it will be a lot faster.
If you use neural network, at the end nobody is going to be guaranteed optimality. So you have a non-convex optimization for training the neural network, so you can't guarantee the optimality.
Actually, it's true that I can't guarantee optimality in general here, but because I cannot say that I found the optimal neural network configuration. But otherwise, there is the universal approximation property of neural networks that tells you that there exists a configuration that gives you the optimal solution up to an approximation. Instead, what you did, basically, you are just using stochastic gradient descent to maximize this function. That's what you are doing, basically. But it depends what is your goal. If you really want to reduce the complexity a lot, you can do it. But then there are millions of other algorithms that you can use to do this. You don't need to use neural network to do that. You can just take any gradient search, any gradient-based method.
I'm not solving one instance of problem.
I know.
Training neural network, it can give you a solution for given parameter. For example, here you have set of parameters. Okay, you train a network which map this parameter to the optimum solution. I am also
No, it's not optimal. That's the point. To some solution.
This approach I played around with power control. Just with only 2 users, if you go unsupervised without label data, like for the secret power control, it's easy to
Okay, guys.
one user.
Sorry, maybe we should discuss offline
Yeah, sure.
because it's getting late. Yeah.
Is there any way you can predict without trying for which class of problems you will use?
In theory, it works for any continuous.
For which it doesn't at all. And so the question is
I
there any single path from trial and error?
So the thing is, so when I say I tried it for beamforming, for example, it doesn't work at the moment. My guess is that if you do beamforming, I'm not sure the map that you're trying to learn is continuous. That's the point. Because then it really depends on the eigenvectors, and then maybe you can jump from one eigenvector to another, and it's a discontinuity. So then could be a reason why it's not working. In principle, it works for any continuous map that you want to learn, basically. So I didn't really look into finding the class of functions for which it works. For experience, I know, so I tried it in many power control problems. It works.
What about problems which you have like the output set?
It's 0, 1.
Continuous, it's like finite.
I tried it just in one case, and that was the next application, and it works. But I have to say, this other case where I used it, so it's user cell association in massive MIMO networks. The problem here was a little bit simpler. The optimization, the map that you want to learn is a lot simpler. So we don't have a lot of time left, so I guess I will go fast on this. So I'm just saying we want to maximize the spectral efficiency of the system. With respect, the variables are this rho jk, which tells you if user k is associated to base station j. Okay, so it's 0, 1. Same approach. This is the neural network that we have used. Okay, let's just go to the results. So this is the CDF of the spectral efficiency with maximum ratio combining and MMSE. In this case, it works. So really perfect match. But I have to say, so I don't really want to enter into the mathematical details, but that problem was a lot simpler than the previous one. So the map that you're trying, this map here is a lot simpler than the previous one. Okay, so it could be that it works for this reason. If you start adding constraints like I want base station J that needs to serve at most k users, at most 5 users, then it might get more challenging. So we didn't try that. This was a simpler setup. But in this last 15 minutes, I just want to show, the application, one application of the other case where you do the 2-step training. And the problem here, in one sense, it's very simple. In another sense, it's impossible. What do I mean? The problem is this: you have a dense network, so these are all base stations, and they have a density, lambda bs, and you want to optimize the energy efficiency of the network. So the network, this time, is the network spectral efficiency divided by the network power consumption. But the problem is that, so the base station have a probabilistic spatial distribution. And the point is that finding a closed form solution for that problem is possible if you assume that the base stations are distributed according to a Poisson point process. So if you take this assumption, you can really, all the integrals in the numerators can be computed and you find a closed form solution. So it's very simple. But the true distribution is not a Poisson point process. So this is the typical assumption in stochastic geometry. You always assume Poisson point processes, but that's not reality. So how to work in this case? We use exactly that approach with the two-step training. We assume a Poisson point process distribution. We solve the problem on paper, and we generate a training set that is synthetic, so based on this PPP distribution, okay? Then it's not that we really measured anything. We just assumed that we chose true distribution for the base stations, which we assumed to be a grid model. So distribution is according to a grid. And then we generated empirical samples following this distribution, okay? So this gives you the small training set, and the PPP gives you the large training set, okay? We use this network, and the input and output are like 1 and 1, because the input, so once you take the Poisson point process assumption, actually the numerator, you average out the channels, because you take the average with respect to the positions. And your only parameter then is the power with which the base stations are transmitting. So that's the input of your neural network. And the output should be the optimal density with which you have to deploy the base stations. So that's why you have 1, 1. So this is simple. For a neural network, this is simple. So we use the small network. But what is interesting, okay, these are the training performance, where we have always we always train over 30,000 samples, but then the synthetic data is 30,000 minus X, and X are your empirical samples. And we tried different numbers from 300 to 30,000. So at most, the empirical data set is 1/10 of the whole data set, okay? And just what I wanted to show in the end is this plot. What is it? So the blue line is the optimal density, which we computed numerically. So grid search, okay? The red line is the two-step approach, okay? So it's basically, there's a mismatch, but it's performing quite well. And then you could ask two questions. What happens if you use only synthetic data? Or what happens, so if the 30,000 samples are all if the 30,000 samples are all synthetic data. Okay, so no empirical, no second step refinement. And that is the black line. And you see that the second step is really important. Otherwise, performance are bad. Another question is, what happens if you use only the empirical samples, the 3,000 samples that you have? Of course, if you train over 30,000 empirical samples, you will have perfect results, but that's not the point. The point is that you don't want to use a lot of empirical samples. So the whole method is, how do I get good results if I don't have a lot of empirical samples? So I have at most 30,000, and I get this green line here. And you see that the maxima here and here are far from that, so which is instead predicted quite well by the deep transfer learning. Okay, so I'm done. Let me just conclude, and then you can ask all questions. Yeah, basically, this is just other applications. So this is power control in massive MIMO systems. This has nothing to do with what I discussed. It's always deep learning, but it's deep reinforcement learning. So this is nothing important. Okay, I'm done. So ask away. Questions? Yeah.
In your public balance control, power allocation,
With the first application.
Yeah, the first application. You said that you train, the solution to your first training step is a vector with the powers for the
Yes.
number of users you have, let's say 7. I think you said.
4 or 7, yes.
Which means that when you actually run this model online, you still presume that you still have 7 users, right? It's not that
Yes.
you can train for 7 and then have that applicable to changes because of exercise.
Yes, yes. What happens if the number of users change?
It's changing like
Yes,
API.
yes. So there are 2 things that you can do. One thing we tried and it worked. Another thing, it's just an idea that we didn't try yet. So what seems to be working is normally you have a constraint in every system. You have a constraint of on the maximum number of users that you can have in a cell. So you train for that number, and then if you have less, you just put zeros in the input, and that works. Another thing that would be, smarter, but I didn't try it. Use transfer learning in a way that needs to be discussed, so it's not completely clear to me. So you train for k users, and you have your neural network for k users. How do I obtain the architecture of a neural network for k plus 1 users without retraining, basically, based on what I know for k users? This is something that, in theory, it makes sense, but I'm not exactly sure how to do this transfer here.
In terms of scalability, I can imagine this might work well for maybe small cells where you have 32 user stops. But
Yeah.
for massive machine type applications with maybe
Too
thousands
many.
of users.
Yes, yeah. Of course. Okay, let me just make another point. So if you have a problem with 1,000 of users and you want to, then you say, okay, forget about the optimal solution. You can always generate a training set with a suboptimal approach. So it's up to you. So it's also to connect with the question before. Of course, there's a trade-off between optimality and complexity. This is what you should do if you want optimality, or at least the closest thing that you can get to optimality with neural networks. Of course, there are a lot of other, if your training set is suboptimal, the best that you can do is that. So your training performance will not be optimal. So that's it. More questions? Yeah.
It's more like a comment.
Okay.
So I think for many of these power control type of problems, in practice you do not have knowledge of all of these channel gains. Typically, now
Okay.
you looked at this 1K interfering user channel. If you now look at the multi-cell setup, you actually don't know anything about pass losses to users in neighboring cells.
In neighboring cells, okay.
Typically, you know because you're serving, you essentially don't know nothing about the other. And so what I think where this kind of approach would make practically more sense is to look into exactly these problems where you have imperfect knowledge.
Okay, I see.
And then you could essentially learn something from what's statistically going on. You don't only observe this through your loss function. It could be a threshold. You could never optimize for energy efficiency, but you could observe through. And in these cases, where you have imperfect observations,
imperfect CSI,
so
basically.
it's so imperfect that you essentially nothing.
Okay, okay. But so to me, that's the point is, if you are in that situation, you cannot even formulate the problem like. So you need to. Yeah. So in that case, you would formulate the problem in a different way, maybe with some expectations or whatever. So maybe with respect, optimize the average of your performance metric if you know at least the distribution of your channels. So the point is, as long as you can formulate an optimization problem, you could tackle it like this. The difference, so in your case, is you don't even have the model, basically. In that case, it's either you can formulate something, or no, this approach. So if I go back to this case, so basically you are in C4. You don't have a model at all.
But you have a model, but you don't know the inputs.
Okay, but if you just don't know the input, you can optimize with respect to the average input. If you know the distribution of the input. Not even that.
I think you can formulate as a indecision problem where you are optimizing agents with imperfect knowledge of the environment, and this is actually what the PIM has been doing. But in that case, you cannot have labeled samples. You go.
In that case, if you don't have labeled samples, you know that.
Maximize the expected sum rate or whatever metric you're interested in using the gradient of the objective function itself.
Okay.
So it's without labels.
But if you don't have the channels, how do you compute the gradient?
You have imperfect channels.
So you have imperfect CSI.
Noisy version.
Imperfect CSI.
Exactly.
Okay, then you could formulate this problem, just taking for example, the expectation of that. Then the framework would be the same. It's just that more difficult objective function.
Yeah, but since during testing time you have different decision makers endowed with different version of the quantity, usually jointly train different networks, such that
It's
during
tough.
testing phase they are not communicating with each other. And this
Okay, then it's a different,
it's completely different. But
completely different approach. Okay, thanks.
Okay,
Okay.
so we're out of time.
Yeah.
Thanks a lot
Okay.
for
Thank you.